Yes. 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 Yeah, see, the point is that we have defined G mu nu as eta mu nu plus H mu nu, right? So it's not that they are separate transformation laws for eta and H. Eta by definition will have to remain unchanged, right? Because H mu nu by definition is G mu nu minus eta mu nu, right? These are you can take this as a definition of H mu nu. Okay, and now suppose you transform G mu nu changes to from eta mu close to eta mu nu to something far away from eta mu nu. Okay. That basically means that the H mu nu will become big. But eta mu nu is a fixed matrix, right?
Suppose if I impose this.
But then that would mean that you are saying there are two fields instead of one, right? But there are not two fields, right? Then you have to write the equation of motion for that field, right?
So can't we treat it like this? So instead of eta mu nu, I will have some general matrix.
Yes.
Which I can consider as some curved background over which I have corrections.
Yeah. But every time you change, right? So say a given transformation is a symmetry, right? Like general coordinate transformation. Here you are saying, and you can only transform those which are dynamical fields, right? Which now, if you say that eta mu nu changes to something else, that also has to be a field, right? Otherwise, how can you change it? See, it's like you are saying that you take a field phi and write it as phi1 plus phi2, and the transformation of phi you will write as independent transformation of phi1 and phi2, right? That will be changing the theory, right? Because then there will be two fields instead of one. So here you are using the fact that eta mu nu is just a fixed matrix, right? So the definition of H mu nu is just this. It may be big or small. If you are looking at an approximation where H mu nu remains small, right, then G mu nu cannot transform too far away from eta mu nu. Right? Then by construction, H mu nu will become big. Right?
This is the definition of H mu nu.
Yeah, this you can take as a definition of H mu nu. Just the difference between G mu nu and eta mu nu. Is this point clear? Right? You shouldn't separately, independently transform eta mu nu and H mu nu, right? Those are not independent fields. Eta mu nu by definition is just a fixed matrix. So this is the definition. Okay? And because of this, we only consider transformations of G mu nu which don't take it far away from eta mu nu. Right? And those are the infinitesimal transformations. Right? Or the transformation parameters will be of the same order as H. Right? That's what it says. Any other question? Okay, so let me begin by writing down the equations that we had gotten last time. So the linearized equation of H had the form and the understanding is that all the indices are raised and lowered by eta, okay, when you are using H. So H rho nu is basically eta rho mu H mu. Okay? That's the way you should interpret this. So this is eta rho sigma. And then we also looked at gauge transformation. which is basically the general coordinate transformation, and that was H mu nu is linearized. Right? We have ignored all nonlinear terms. Okay, so terms of order h squared, epsilon square or epsilon h, those terms have already been ignored in this. And our goal will be to try to find the solution to this equation with this gauge invariance in mind. Okay, and this will be similar to what we do in electrodynamics, right? The way you find plane wave solutions in electromagnetism. Okay, you write the equations of motion and also gauge take into account the fact that there is gauge symmetry. So this gauge symmetry is normally dealt with by saying that we impose a gauge condition. So this means that we have to impose a gauge condition. Okay, like in electrodynamics. Right? In electrodynamics, this is the Lorentz gauge condition that we impose. We want the analog of this condition. Okay. But with one difference, which is that in the case of electromagnetism, okay, the gauge transformation had the form where there is one function epsilon of x that was responsible for the gauge symmetry. Here you see that there are actually four functions because epsilon is a vector. Okay. So there are four functions, okay, which are responsible for gauge transformation. And because of this, you have to impose four conditions and not one. Right? Because the four functions can be used to fix four arbitrary combinations of range. Okay. Of course, there are many choices, right? Like in electrodynamics, you could. This is just one choice. This is Lorentz gauge. Right? You could have used Coulomb gauge, for example. Right? But it's always one function what of conditions that you impose. Here you have to use four function what of condition, and one convenient gauge that is the analog of the Lorentz gauge in electromagnetism. Okay, is what is called the Didonder gauge. This gauge, in fact, is imposed without making linearized approximation. So the general form of this gauge is this. This corresponds to four independent conditions because rho can take any of the four values. Okay. Mu nu indices are contracted, but rho can take any of the four values. So this corresponds to four independent gauge conditions. Is this point clear? So what we are going to do is that because we are working in a linearized approximation, we have to linearize this gauge condition. Right? We have to see what it means for linearized in the linearized approximation. So this one, so in the linearized approximation, we can replace g mu nu by eta mu nu because this already has eta. Okay, this involves derivative. So we have eta mu nu times half, and have to write the expression for this gamma rho mu nu. So is this clear? Yeah, this is the expression for gamma rho mu nu. And again, we have used linear data approximation. All the raising and lowering of indices we are doing at eta. Okay, so only the derivatives, okay, because they act on G, and the leading term in G eta doesn't contribute, right? Derivative of eta is 0. So you already get a derivative of H because the derivative acts on G, and then everything else is eta. So this I can write as these two terms are the same. So I've just used the fact that these two terms are the same. So and this mu is raised up, so I can write it this way: minus half del rho H mu equal to 0. Okay. And now the idea is that you are going to use this gauge condition to simplify this. Okay, just like as we do in electrodynamics, right? Once you impose this Lorentz gauge condition, the Maxwell's equation, right, can be just becomes box mu equal to 0. Right? That's what happens in the case of Lorentz gauge, and we will see that something similar happens here. So you see here, let me write this maybe in a slightly different form, okay, which will become, I can write this also as just by exchanging various indices. H is symmetric, right? So I basically it says that one derivative gets contracted to one index of H, right? That's the content of this. Okay, so here also one derivative is contracted to one index of H. And here the two indices of H are contracted, right? That's what it says. So it's just changing the name renaming the indices. Okay, but it will be easier to apply in this form here. Let me put it like this. So you are going to use it to simplify this, and we see that the second term has that structure, right? The third term also had that structure, right? Except the nu and mu indices are exchanged. So once you use that equation, this equation becomes box H mu nu minus half the last equation, last term we keep as it is. Okay, now you see that these two terms are the same and exactly cancels the last term. So I can cancel these off. And what we get is box H mu nu equal to 0. Okay, this is like what we had in electrodynamics, box mu equal to 0, right? After you use the Lorentz gauge condition, Maxwell's equation reduces to box mu equal to 0. And this solution, the solution to this is H mu nu equal to some E mu nu e to the I k dot x, k square equal to 0. Yeah, but metric is also a field. You can think of the metric H mu nu as a field, right? As a dynamical field. So H mu nu is basically playing a role of A, right? So gravity metric you think of as describing the geometry, but you can also think of this as a field. Right? Because after all, Einstein's equation tells you how the metric, what kind of constant you put on the metric, right? Just like the field equations do in Maxwell's theory. Okay. So the fact that the metric encodes geometry is an extra ingredient, extra information, but metric is also a field, right? So anything that you do in dealing with fields, you can apply on the metric as well. Exactly, that's right. Okay, so once you have written the Einstein's equation, right, then while doing all manipulations, you can forget about the fact that it measures distance. Later on, when you ask how to detect some changes, then you use the fact that this actually measures distance. Okay, and we will see when we discuss the detection of gravitational waves, we will make use of that information. Is this clear? Now, you have to impose the gauge condition, right? Just like in electromagnetism, after you get mu equal to epsilon mu to the I k dot x or e mu to the I k dot x, you have to impose k mu mu equal to 0, right? Because that's the gauge condition. So similarly, you have to impose this gauge condition. So this gauge condition now tells us that, or this gauge condition doesn't matter, this one, that k rho e rho nu equal to half this. Okay, so the main difference here compared to electrodynamics is that instead of having a vector that labels the polarization, right, you have a tensor that labels the polarization. This is like the polarization, right? This is E mu. Pardon? No, then X dependence all here. Just like what happens in electromagnetism, right? You have some E mu nu and then E mu e to the I k dot x. Now, first of all, you can see that this fact that it appears as e to the I k dot x, right? The same way it appears in electromagnetism, tells us that these waves that we are seeing propagate at the speed of light. Is that clear? Right? It's kx minus omega t, right? Or x minus t. It basically goes as this quantity, right? If you imagine that k is along the third direction, right? It's the overall factor of k times x3 minus t. Right? So when you change t and change x3 by the same amount, the waveform remains the same. So it propagates with the speed of light. So gravitational waves propagate at the same speed as light. Yeah, because this, if you look at this, okay, in electromagnetism, right? How do you know that it travels with the speed of light? Because you have this dependency to the I k dot x, right? And if you take, for example, the k to be along the third direction, k0, let's say omega 0 0 omega, right? Then this is e to the minus I omega t minus x, right? T minus x3. This means that if you change t by some amount, epsilon, and change x3 by the same amount, this phase remains unchanged, right? So the speed is 1, right? Then 1 means c in this case, right? Because you have set c equal to 1. And it's the same structure that holds also here. Right? This dependence is exactly identical. That's what tells us that gravitational wave travels at the speed of light.
So when it, because there is no master.
When?
There is just box. No master.
Yeah, exactly. Right. It's related to the fact that there are mass terms.
So when it comes to every, then automatically the speed of GW will also reduce. So the over the speed of light.
Well, I mean, this is for in a vacuum, right? I mean, we are not saying that the speed of light, speed of the gravitational wave should reduce. See, this calculation is in the background where G mu nu is eta mu, right? Okay. So it's not that the speed of light and speed of gravitational wave is the same in the medium. Right? Inside a medium, things can be different.
Say like in relativity, there is no notion of velocity also. Mentioning like this is the speed of gravity. So here is there a clear-cut notion of velocity?
There is. I mean, if imagine that there is a event which emits gravitational wave and at the same time emits a flash of light. It's a physical question whether we will observe the two events at the same time or not, right? Suppose you have a gravitational wave detector and one light detector. Yeah. So the point is that assume that it travels in the vacuum, right? If it goes into the medium, then things may be more complicated, right? But because this fact that it goes into the I k dot x for electromagnetic wave, right? This is also in the vacuum.
In that one case, generally we say this is the GT faceless transmission when we define the amplitude of the data. But
Yes.
all that is contained in this one gauge.
Yes, indeed. It's contained in one gauge. Okay, there is more. Okay, there is a little more. We'll discuss this. The point is that just like in electromagnetism, right? There is a k dot epsilon equal to 0, right? That comes from the Lorentz gauge condition. But there is also a residual gauge symmetry that allows you to shift epsilon by k. Right? Using that, we can constrain it further. Right? Because k dot epsilon equal to 0 gives you one condition, right? On a 4 vector. Right? But actual polarization is characterized by only 2 vectors, right? So this using this residual gauge symmetry, we can further constrain it, right? And choose this to be if the wave is propagating in the third direction, we can choose epsilon to be either in one direction or in two directions. So there is a similar event which will happen here. Well, I mean, after what are conductors and insulators after all, right? Charge particle motion, right? So the properties of conductors and insulators, I mean, you can explain just by motion of charge particles, right? Except that the charge particle moves in different ways in conductor and insulator, right? In one case, it can move freely. In the other case, it's bound. Here, the analog of that here will be how the matter responds, right? When gravity wave propagates, for example, right, through matter, it can displace the matter, right? But that matter may be subject to other forces, right? And now it's a question of either matter is freely displaced or whether it's somehow bound by other forces, right? And that will make a difference between how the gravity interacts with matter. Right? The physics, of course, the actual events will be very different, right? There might be analogs of conductors and insulators, but the what distinguishes conductors from insulators is basically how the charge particles are move, how the charge particles move inside a given material. And analog of that will be how the masses move inside a given material, because those are the sources of gravity. Any other question? Okay, so let's now check whether the gauge transformation this one, what happens to this gauge transformation when you impose this, right? So gauge transformation is h mu nu going to this translates to e mu nu going to e mu nu plus let me call this okay. Basically, I have taken epsilon as minus I so when you take the derivative of epsilon, right, then you get bring down I k nu, right, and that's why it has become k mu xi nu plus k nu xi nu. Yeah, this is exactly what happens in electromagnetism, right? You take a gauge transformation which is of the form I minus I times e to the I k dot x, and then when you take the derivative, you shift by k mu, right? K mu times some function, some arbitrary constant. Here it's k mu times I nu plus k nu plus I mu, or these are arbitrary vectors. This is analog of gauge symmetry. Whether it's a residual gauge symmetry, we'll see, right? Because now we have to check, right, what happens to this, right, when you substitute here, right? Whether, see, suppose we have a E mu that satisfies this, right? Now you are asking that we replace that E mu nu by this. Does it satisfy this still? Right? If it does satisfy this, right, then this is a residual gauge symmetry, right? Because you can once you have gotten an E mu nu, you can still transform it by this. Is that clear? So you have to substitute this there and check what happens. I can do this here. So we are looking at this equation, right? This is the equation we are looking at. So the left hand side of this equation changes by k rho e rho nu, right? So k rho times this, k rho times k rho xi nu plus xi rho k nu, which is k square is 0. So first term goes away. The second term gives you k dot xi times k nu. Okay, we have used the fact that k square is 0. The right hand side of star changes by half k nu e rho rho. So half k nu, and how much does e rho rho change by? This is k dot xi plus k dot xi. So what we see from here is that this equation, the left hand side and right hand side, changes by exactly the same amount. So if we had found an E mu nu, which satisfies all these conditions, this condition, then under a gauge transformation, a gauge transform version of mu continues to satisfy that condition. This is true only when equations of motion are satisfied, right? You see that we are use crucially the fact that k square is 0. So this gauge choice is good enough for getting the equation of motion, right? It's not that you have not gauged, you have not done anything, right? When equations of motion are not satisfied, right, then this actually restricts the field configuration. But once you have solved the equation of motion, then you see that these acts as residual gauge symmetry, right? Because this now preserves this condition, gauge condition. Is this point clear? So let me summarize the conclusion of this from this. First is the solutions to equation of motion in Didonder gauge. Linearized equation of motion. Subject to the condition that k rho E rho nu is equal to half k nu E rho rho. But this has residual gauge symmetry. For any vector. So this question of whether you can use the transverse restless condition, right, essentially follows from this. Okay, because of this additional symmetry, okay, you can use this, right, to see that. Take E rho rho, right? How does it transform? E rho rho transforms to E rho rho plus 2k dot xi, right? And then you just adjust your xi so that it cancels E rho rho. It just makes E rho rho equal to 0. Then it becomes stressless, right? Once you have made E rho rho equal to 0, then this equation tells us that it's transverse, right? K rho E rho no equal to 0. Right? That's what is called a transverse gauge condition. Is this point clear? Are there questions?
So basically, this expression is particular k rho E rho.
Yes. So this is a consequence of the gauge condition. This is the analog of the k dot epsilon equal to 0.
So that will be like the propagation vector and the displacement. The propagation vector and the displacement, the perpendicular. So that is a physical nature.
Yes, exactly.
Similarly, here like here is there any physical, the same is physical nature.
Yeah, the propagation and the displacement and displacement. Okay, it's not a question of what you mean by displacement, right? Is the electromagnetic field, right? They are transverse. It's the same thing here, right? E mu nu, if you think of it as a gravitational field fluctuation, right, that's transverse to the direction of propagation.
Until when zero rho is not equal to zero,
Yes.
That will become only zero when we impose the additional.
That is true. Yeah, yeah. But the point is that this by itself, right, is not significant because this depends on the choice of gauge. Right? After you have combined these two, right, just like in electromagnetism, in Lorentz gauge and Coulomb gauge, right, unless you use the residual gauge condition, right, the initial condition that you get in Lorentz gauge and Coulomb gauge are different. Right? Only after you impose a residual gauge condition that you see that they have the same content. The same thing is true here, right? I mean, this by itself, right, you have just imposed the gauge condition, but you have not made use of the residual gauge symmetry. Yeah, so that's a gauge dependent statement.
So once we include that residual gauge symmetry also, then we can physically interpret it.
Exactly. Right. So the physical interpretation, for physical interpretation, right, what the polarizations are, you have to take into account the fact that there is also a residual gauge. Right? Otherwise, different gauges will give different answers.
Just like in sources, we don't have.
That's it. Yeah. So sources, I mean, we are not considering only the absence of sources. Transverse. No, not transverse gauge. Oh, I mean, it's just once you impose. So the traceless transverse condition means that E rho rho is 0 and K rho E rho is equal to 0, right? Now that condition does not follow from here. Right? If it's traceless and transverse, it satisfies this because both sides vanish. Right? But this by itself doesn't satisfy that condition. Right? Doesn't impose that condition. But the point is that using this residual gauge symmetry, you can make E to be traceless. Right? Because E rho rho shifts by K dot to K dot psi. Right? Once you made E traceless using this residual gauge symmetry, then it follows from here that the left hand side also vanishes, right? And it becomes transverse. Exactly.
Is that unique? Does it completely fix it?
No, we'll see how what completely fixes this freedom, right? We have to do some counting. Right? Let's do some counting because K dot I equal to 0 certainly doesn't fix I completely, right? So there is certainly more freedom than that. Okay, so let's count how many independent polarizations we expect, right? Physical polarizations. Okay. So for that, let's again go back to electromagnetism. Right? In electromagnetism, to start with, we had a 4 vector that levels the polarization, right? Epsilon into the I k dot x. Then the gauge condition k dot xi equal to 0 gives one condition. Right? It reduces from 4 to 3. And then the fact that there is a residual gauge symmetry means that you can just impose another condition arbitrarily. Right? Because the residual gauge symmetry allows you to change things without changing the physics. So that brings the number of independent physical polarizations to 2, right? 3 minus 1. Okay. So let's do a similar counting here. Okay. So to begin with, how many independent components did you have before you impose any gauge condition or residual gauge symmetry? 10, right? 4 by 4 symmetric matrix. Right? That is 4 times 5 by 2, right? 10 independent components. Then the gauge condition corresponds to 4 independent conditions, right? So that gives you 10 minus 4, which is 6. And then there are 4 residual gauge symmetries that is encoded in the xis. So that brings the number from 6 to 4 to 2, right? Because 6 minus 4 is 2. So number of independent polarizations, is 10 minus 4 minus 4, which is 2. So that's basically the same as in electrodynamics. This one. Okay. So to begin with, you have 10 independent components, C mu nu, right? Because 4x4 symmetric matrix. Then we had these conditions, right? How many conditions are there? You see, nu is a free index here, right? Rho is contracted. So there are 4 conditions. Right? That's this -4. And then we said that after you have imposed that condition, right? Given any E, we can get another E by this, which is physically equivalent. Right? There are 4 vectors here. Xi is an independent vector, right? Okay. So that means that 4 of the degrees of freedom are trivial, right? You can change it by gauge transformation. So that gives you this -4 again, right? And this is 2. So you should be able to label your solutions to the equations in terms of 2 independent polarization tensors. That, and we will now explicitly construct those 2 independent polarization tensors. Okay, of course, the choice is not unique because given any choice, one choice, you can always transform by this, right? And that is an equivalent choice. But we'll just give one solution for these 2 independent polarizations. Is it clear? Are there questions? So let's take K to be along the third direction. Where this is some arbitrary number omega. So we start with E mu nu, right? So let's look at the K dot K. So we have the equation K rho E rho nu equal to half K mu E rho rho. Okay, first of all, we have chosen this, right? But this is in a sense completely general because this is saying that you propagate in third direction. Right? But if you propagate in any other direction, right, the result can be obtained by rotating the coordinate axis. Right? So once you know how to do it for third direction, wave moving in third direction, you know how to move it for general waves. So let's look at the solutions to this equation. What condition does it imply? Does this imply? Okay. So for nu equal to 1, okay, this will be a simpler one. For nu equal to 1, the right hand side is 0. Right? So we get E. Okay, I'll write it in a K rho E rho nu. And here I'll put it as K nu. Okay, this form that I have taken will be the upper index. Right? It's important to say whether it's upper index or lower index because lowering the index will change the sign of this, right? So this omega is K with upper 0. So for nu equal to 1, we have K upper 0 E0 1. So that gives to omega times E0 1 plus E3 1 equal to 0. Yes, thank you. Because for nu equal to 1, it doesn't matter because this is 0. Nu equal to 2 also a similar equation. Omega E02 plus E32 equal to 0. For nu equal to 3, we get omega times E03 plus E33 equal to half K3. K3 is same as omega. And E rho rho I can write as minus E00 plus E33. plus E11 plus E2. Yes, minus plus plus plus. That's why you see the minus sign here. And for nu equal to 0, you get omega times E00 plus E30 is minus half omega, because K with lower 0 is minus omega, right? Minus half omega times the same thing. Please, right? Let me just check. Okay. So let's subtract these first to get rid of the E03. E03 is the same as E30, right? E is symmetric. So subtract the two equations. So omega, okay, omega cancels from both sides, right? So we get E33 minus E00. Okay, we have subtracted. Here we get half. You see, when you subtract this, this becomes plus, right? So equal to, okay, minus half E00 and then another minus half E0. Okay, so minus E00 plus E33 plus E11 plus E22. Okay. So you see that E33 minus E00 drop out, right? And so this gives you E11 plus E22 equal to 0. Okay. The other combination is when you add them. When you add them, these terms just cancel. So they are just opposite sign. So when you add them, so let's call this equation 3 and 4. Right? So this came from 3 minus 4. And when you take 3 plus 4, you get this to give you 2 E03 plus E33 plus E00 equal to 0. So we have got 4 conditions, these two and these two. So these 4 conditions have to be imposed, right? There are 4 other conditions, right, which are somewhat arbitrary, right, because those come from the freedom of shifting. We know that at the end we should be left with 2 independent polarizations, right, just from the counting. So if we can find 2 solutions that satisfy these 4 conditions, that's good enough for us. Then those are solutions in some gauge, right, with some choice of the shift parameters. Right? So you need to find 2 solutions. So let me write down the 2 solutions. So solution 1 is E11 equal to minus E22 equal to some E say, rest are 0. Let's check if it satisfies these equations. This is okay, right? Because these are all rest. This is okay because we have taken 2 to be negative of each other, and this is also okay. Right? These are all rest of the e's. So this is one solution. Solution 2 is E12 equal to E21 equal to E, and rest are 0. No, this is not related to that fact. We have gotten 2 solutions, right? To argue that these are all the solutions that we need the other fact that there are only 2 independent degrees of freedom, right? So once you have found 2 independent solutions, we are done. See, if we just impose these 4 conditions, right, there will be 6 independent solutions, right? Because 4 linear equations in 6 variables, in 10 variables, right? We are just finding 2 of those solutions, right? There are 4 other solutions to those equations. But the point is that you don't need them because you have argued that as long as you find 2 independent solutions, we have got everything. Exactly. Other 4 can be obtained from these by adding things like this. They are arbitrary in some sense, right? Yes.
So basically what I'm asking is how do you know that solution? So
Okay.
these will be valid choices only if you can find some side.
No. Okay. Our goal was to solve this equation, right? We have solved it, right? Now you are saying that given a solution to this, okay, there are other solutions, okay, which are obtained by this. Okay. So, okay, or let me put it this way. Suppose you are trying to find the 4 other independent solutions, right? You start with mu equal to 0. Okay, and just transform like this. Take the solutions to be of the form k mu xi nu plus I nu k nu xi nu. Those will be 4 independent solutions, right? Is that clear? Because xi can take any value, right? So the 4 independent solutions you can trivially get by simply taking this to be 0. See, mu equal to 0 is clearly a solution, right? Of all these equations, all mu equal to 0. That's clearly a solution, right? We have already argued that once you have gotten one solution, you can generate others by this shift, because this shift automatically satisfies all these equations. You can verify it, but we verified it in general, right? because this condition, right, is satisfied by this combination. So anything of the form k mu xi nu plus k nu xi nu, right, will automatically give a solution to these equations, right? So there are 4 of those, right? And you have found 2 more. So those are the 6. Only thing you have to worry is that whether these 2 are part of those 4, right? Then you have not found everything. Exactly, right? And that you can check, because this, look at this structure, right? It should have at least one index that is k mu, right? K mu goes in the only in the 0 and 3 direction, right? Whereas the polarization that we have chosen are in only in 1 and 2 direction, right? So it's impossible to get those polarizations from this structure. Right? That basically shows that these solutions that you have found are not of this kind. Right? So the six independent polarizations that we are looking for, 2 of these are these, and the other 4 are of this form. Okay, of these are not useful because they are like the pure gauge, right? You can always take epsilon mu proportional to k mu and get a solution to the gauge condition in electrodynamics, right? But that you know is not a physical polarization. Because these are the physical polarizations of the gravitational waves.
Alternative polarization. They also talk about like 6 kinds of polarization. They will include like 2 tensor modes, 2 vector and 2.
Yes.
Yeah, so that number 6 is also coming without including this residual gauge.
Yeah, but those we need when there is matter field present, right? Those modes get determined by the matter background, right? In that sense, those are not independent variables, right? They are determined in terms of the source.
So far we detected only this tensor modes.
The gravitational waves are to detect are always tensor modes because you are detecting them in vacuum. You are not measuring inside the star, right? I mean, you are seeing it in far away, right? So those are always the tensor modes, right? They're just like the electromagnetic waves that you detect from far away sources, right? At the standard polarizations. Yeah, in cosmology, for example, we will see, right, that these modes are important. That you have to keep track of these modes, right? Not that they do very much, but you have to keep track of these, right? You cannot just set them equal to 0, then you will run into inconsistency. Other questions? So these have names, right? This first one is called plus polarization, and this one is called cross. Okay. And this has to do with how it stretches things. Okay. If you think of the one as the horizontal axis and the 2 as a vertical axis, right, then the plus polarization basically says that as the wave passes, right, when U11 is positive, E22 is negative, and vice versa, right? Because of this. U11 positive means what? That it adds to eta 11, right? 1. So that means the effective distances get stretched, right? They become bigger because you are measuring the distance by the metric 1, which is eta 11 plus H11, right? So when H11 is positive, effectively the 1 component of the metric becomes bigger. So you'll see the bigger distance. Okay? And at that time, the transverse direction, the 2-2 direction, you'll see smaller direction distance in a 2 direction because H22 is negative. Okay? And vice versa. Okay? So the plus polarization gravitational wave, when it moves, right, you will see that the way the stretching happens is that when one gets stretched this way, two gets compressed, and when two gets stretched this way, one gets compressed. Is this clear? This one you have to do a little more work, right? You have to diagonalize a metric, because when you have this present, right, the metric in the 1-2 plane, the metric has two diagonal entries, 1 1, and two off diagonal entries, right? EE. Okay. So you have to diagonalize and see what this gives, and you'll basically see that that's roughly the same as this, except that the angle it's 45-degree turn angle, right? That when this direction gets stretched, this gets compressed, and when this gets stretched, this gets compressed. Is this point clear? Well, that is true in light also, right? I mean, you can only change. Okay. Here you can say you can only see the change in the electromagnetic field, right? Except that the change there is the same as the value of the electromagnetic field, because in the vacuum electromagnetic field is 0, right? Here in the vacuum the metric is non-zero, right? Because eta 1 1 and eta 2 2 are all 1, and you are seeing the fluctuation on top of that. Yes.
Can we get some stretching in time direction?
Yeah, you can, right? But it's like that's like general coordinate transform. Well, after all, residual gauge metric is part of general coordinate invariance, right? So it basically says that if you take this form, right, and then mix up the time and space direction, right, that's what we'll see. Because clearly here, I mean, when we say that the polarization is going this way, right, you have a specific notion of what is time and what is space. But general coordinate transformation can change that. So these solutions, and another of saying that just these solutions, right, these polarizations, you can say, okay, what do they represent, right? These also correspond to fluctuations on a battery. Okay? But those fluctuations are the same as it. You take eta mu nu and make some general coordinate transformation with time dependent coordinate transformation, and you will see some oscillation in the metric, and those are those. Yeah, so let's take this, right? Let's take a solution where you have k mu I nu plus k nu I nu e to the I k dot x. This is also a solution to these equations, right? So you can say, okay, suppose a wave like this comes and passes you, right? It looks like you will see some stretching and contraction, right? By the same kind of argument. Okay, but those stretching and contraction you can show, okay, and it follows from whatever the way you have arrived at this. There's those stretching and contraction, okay, basically corresponds to taking the usual flat space time and making a change of coordinate which has this kind of oscillation. Okay, you can in fact work out what kind of change of coordinate corresponds to this. Right? Eta mu nu plus this is equivalent to eta mu nu, right, but written in a different coordinate system. So these waves, right, are just a reflection of the fact that you have chosen the coordinate system which is oscillating. Right? Not that there is actually a physical oscillation that is going on in space. Where these are genuine stretching and contraction in space time. Any other question? Okay, so let me now describe the direction. So first I'll describe the direct detection, even though this came much later, right? Actual gravitational wave was indirectly detected much earlier, okay, but I'll discuss that later. Okay, first direct detection. Okay. And this is done by the laser interferometer. So let me explain the. So the setup is that we have a laser beam coming in, then there is some kind of mirror, okay, at 45 degree, okay, which splits, which sends half of these beam through and half in the perpendicular direction. Okay. And then there are two reflecting mirrors here. Okay, so light comes, goes back, and then they again get, this gets transmitted, this gets reflected, and you combine them. Yeah. So here in general there will be interference, right? Because you have two beams which are coming in, right? And whether it's constructive or destructive interference will of course depend on the relative length between of this and this, right? If they are, and so that you have to take into account. So the way the experimental apparatus is set up is that if when nothing is happening, okay, in flat space time, you adjust this length so that there is destructive interference here. You don't see anything. Okay, so you have a detector that detects the signal. Now, let's suppose, let's ask what will happen. Suppose there is a plus polarization. Let's say this is the one direction, this is two direction. Suppose there is a plus polarization, okay, that passes through in the direction transverse to the this plane. Then what's going to happen is that as that passes through, okay, this may contract and this expand and vice versa. Okay. When that happens, these two lengths, the relative values of these two lengths change, right? In fact, they start oscillating. And as a result, the interference pattern here also starts oscillating, right? If it has a destructive interference before, right, once when the gravitational wave is passing through, right, you will see oscillation because the interference pattern, these relative lengths keep changing. Okay. So that's the detection. Okay, this is the way we detect gravitational waves. That when the gravity wave passes through, you see how much the interference pattern is changing, and you see an oscillation in the interference pattern. Okay, and that's the signal of gravity waves. Now, of course, you have set up your detector, right? I mean, you cannot guarantee that the gravitational wave will come like this, right? If it comes like this, you are lucky. Okay. In general, it may come from some arbitrary direction with some arbitrary polarizations, right? And that you can work out how much will be the change, right? If you are extremely unlucky, then you will not see any change, right? Imagine that the polarization is the cross, right? Then you can check that you will not see any change in the detector, right? But in general, right, it will come from some direction with some polarizations, and that will have some pattern. Okay, and that's what you observe. Right? So this is the way the gravitational wave detector works. So in the homework, you will have some problems where you have to calculate this oscillation when the direction of incidence is not perpendicular but from some general angle. No, if it's cross, right, and if you had set up your apparatus in this plane, right, then you will see the cross polarization, right? So in general, if you have a given polarization falling through, right? Which may be a linear combination of plus and cross, for example, right? In that case, what will happen is that you can work out how much will be the stretching and contraction, right? Because we are given the metric, right? Your detector is in some other direction, right? Not in the direction in which the stretching is taking place, but not necessarily in the completely or 45-degree angle, right? And so you'll have some effect, right? But not be the maximal effect. If it happens to the plus polarization, you will see the maximal effect, because, right? Because those are the eigen directions. Otherwise, you have to work out exactly how much the change will be. So imagine that the metric, suppose you have a plus polarization has come, E minus E, right? These are oscillating. But your detector is oriented in some other direction, right? Imagine the detector is oriented at an angle theta. These are of course always perpendicular, but imagine that this angle is theta. Then you can only detect that this is the length that is relevant, right? But since the metric is given, right? The metric is 1 plus this, right? So the metric is given, you can work out with this metric how much oscillation this will have, right? And how much oscillation this will have. What is relevant is the difference between these two lengths, right? And that will determine the strength of your signal.
Sort of defined with respect to the configuration of my.
Exactly, that's right.
And if it's crossed, then it will be reversed.
Exactly. Yeah. Imagine that your measurement device, you declare that once you have fixed your measurement device, then the plus is the one which gives a maximal strength, right? That fixes axis 1 and 2. Right? Now you take another gravitational wave, right? Which may be cross, in which case you will not see anything. But in general, it will be oriented in some particular direction, and you may see some signal, right? In fact, there is no reason why it should come in the perpendicular direction, right? It may come at an angle, right? In which case also the stretching will be different. No, because if it's a cross, right, then you can show that it will not detect. It will not detect, because what will happen is that the length in this direction it may oscillate, right? But the two transverse directions will oscillate in the same way. Right? That this one and this one, right, will change in the same way, right? Then it doesn't, because it's the difference which matters, right? Yeah. Exactly. So the point is, you also have an idea of which direction it came from and so on, right? Because there are multiple detectors from which you can reconstruct the source. So the way one does it is that you actually look at the way detection goes, right? It's not that you detect and then try to reconstruct, right? That you first take a arbitrary binary black hole system, right, and see what kind of emission there will be. Based on that, you calculate what your detector will detect, right, at some angle. So you have a lot of templates, right? If a particular black hole configuration merges in one direction, right, this is the signal that you will see. If it merges in another direction, this is the signal you will see. If the angular momentum is a little different, this is the signal you will see, right? So you build a lot of templates, and then you match your observation with those templates to figure out what is the most likely configuration, likely event that gave rise to this particular event or particular signal. Right? Going the other way is much more difficult. To actually reconstruct what happened just from the signal. Okay, so let me now describe the indirect detection. And these basically follow from the fact that gravitational wave carries energy. Okay. So the gravitational energy, if you recall, okay, I describe how you do it. That namely we write R1 mu nu, there's a linear term minus half R1 eta mu nu is equal to 8 pi g times T mu nu plus T gravitational mu nu. Where this T gravitational mu nu is basically everything that came from the nonlinear part of this. Okay, that's how I define this T 8 pi g T gravitational mu nu.
The linear terms in gravity is forced by the non-linear.
Exactly, that's right. Okay. And because usually energy is the source, energy momentum tensor, whatever those nonlinear terms are, you declare them as the energy momentum tensor of the gravitational wave. Okay. So this contains quadratic and higher order terms, okay, which you can work out by, because you know the expression for the Ricci tensor, right? You just expand it out and pick up the quadratic and nonlinear higher order terms. And if you work, this is a long exercise, but you can, it's a straightforward algebra. That if you try to, that the quadratic terms in T gravitational mu nu gives the following expression for the energy momentum tensor of the gravitational wave. Yes, I'll explain what this is. Right. So you see, the gravitational field is fluctuating, right? It's space and time dependent. So if you actually calculate the energy momentum tensor, you will find that it has oscillation. This basically means that you either do space averaging or time averaging. It doesn't matter what averaging you do, right? Over a period, for example, right? So you can take this as a time average. Okay, if you take the time average over a period, then the oscillating part goes away. The oscillating part of the energy momentum tensor, and we get something like this. Okay. And if you have done the calculate the energy momentum tensor that is carried by the electromagnetic wave, right, there is a very similar expression. There is of course no 1 over 8 pi g, because 1 over 8 pi g came because we declared this 8 pi g times this has that, right? So the expression for this had 1 over 8 pi g. Okay. But otherwise, the electromagnetic wave, the energy density that the electromagnetic wave carries, has this structure of k mu times mod u1 square plus mod u2 square. Okay, where these are the two polarizations. So this basically says that the gravitational wave carries energy. Okay. So if a source is emitting gravitational wave, it loses energy, right? Because the total energy is conserved. In fact, you saw that this quantity, right, satisfies the usual conservation law that you are familiar with in flat space, right? Not with covariant derivative, but with ordinary derivative, ordinary divergence. So on this, we can apply energy momentum conservation as we will do in flat space, right? Just think of this gravity, the h mu nu is another field which has some energy momentum tensor, and then the total energy momentum for the field plus the source should remain constant. So the way this was used, okay, is this binary pulsar experiment. So a pulsar is basically, you can think of some object in the sky which gives out signal at regular interval, short intervals. What it is, you don't need to know. We don't need to know for this class, right? It's some object which gives out signal at regular intervals. A binary pulsar means that it's a binary system, one of which is a pulsar, which gives rise to which gives out signal at regular interval. Now, when you have a binary pulsar, so suppose this is a pulsar, okay, this is some companion, and the pulsar is rotating around the companion, right? They are rotating around each other. Just think of this as the Newtonian system, right? You don't even have to think of this as in the general relativistic terms. Okay, they rotate around each other. And suppose we have an observer, this is us, right? We are looking at the pulsar. Now, even though the pulsar gives out this signal at regular intervals, because of the Doppler effect, we will see that the pulse interval actually varies. Because when it's going away from us, we will see that the interval is longer. When it comes towards us, we will find that the interval is smaller, right? Higher frequency. So by seeing how the pulse, the interval between the pulse varies, we can figure out the period of this orbit. Right? There will be an oscillatory variation of the period, right? We can figure out the period of this orbit. Okay? So this way we determine the period of a binary system, right? Binary pulsar system. So pulsar is important because that allows you to detect the period with good accuracy. Now, when this is rotating around each other, we expect that this will emit gravitational waves. And if this distance is not close to the Schwarzschild radius, right? Imagine the distance is large enough. Then you can ignore the effect of the energy momentum tensor due to gravity of nearby system. Just think of this as two classical sources, point masses rotating around each other. Just think of this as a Newtonian system. But that determines the orbit, right? Once you have gotten the orbit, you have the energy momentum tensor of the orbit, right? Two delta functions. One delta function for this, another delta function for this. Okay, but the delta function is located at a point which is accelerating, right? Which is changing with time. So you substitute that in the Einstein's equation. Okay? So substitute in the Einstein's equation. You can just do it as linearized Einstein's equation, right? You don't really need more than this in the first approximation. So this problem becomes more or less the same problem as calculating electromagnetic wave from a source. Right? The only difference is that instead of having a mu, you have a h mu nu, but the mathematical difficulty level is the same as that of calculating electromagnetic wave emission from a source. Okay, from a there you have a charged particle moving around each other, two charged particles moving around each other. Right? Here you have 2 point masses moving around each other. So you can calculate how much gravitational wave it's going to emit in all directions. And once you have calculated that, you can use this formula. I did that formula, but you can use that formula to find out the total flux of energy. Right? Take a big sphere around this system and calculate the total flux. That tells us the rate at which it loses energy, right? By emitting gravitational waves. Is that clear? So once it starts losing energy, right, then again you can go back to Newtonian physics, right? If you have an orbiting system and if it loses energy, what's going to happen to the orbit? It's going to shrink, right? It's going to come closer. And as it comes closer, the period will increase. Right? So this says that because of the emission of the gravitational wave, there will be increase in period of the binary pulse. And of course, for any binary system for that matter, right, except that you need a pulsar to detect the period, right? How much it changes, that for that you need the pulsar. Otherwise, any binary system will have this feature that it will start collapsing, right? The orbit will start shrinking, and the period will increase. And of course, you can observe this binary system for a long period, right? As long as they don't, as long as they survive, we can observe it, right, over many years. And using that, we can figure out how much the period is changing. And that you can compare with what you calculate based on the energy flux. And you find perfect agreement with what Einstein's theory predicts, right? Using Einstein's equation, you can figure out how much energy flux will be emitted. That tells us how much, what is the rate at which the period will decrease. And you find that that exactly agrees with what you observe experimentally. So this observation was done much earlier than the detection of gravitational wave. Direct detection happened only recently, right, or relatively recently, within last 10 years. But this detection was done in the late 70s or early 80s, right? This agreement with the gravitational wave. So in a sense, we already had indirect evidence that the gravitational waves are real. They do what they're supposed to do. And the recent experiments detected them directly using this laser interferometer. Okay, I think I'll stop here. Are there questions? For this, okay, you can determine the gravitational field, right, by integrating the source. Just the way you determine electromagnetic field from a source, right? Okay, so take a big sphere. You have determined the time varying gravitational field there, right, which is of the form of a gravitational wave propagating out, and then you use this formula for T mu nu, right, average T mu nu, right, and using that you can calculate the flux of energy to that surface. Right, and it doesn't matter which surface you use, because of the fact that this T mu nu satisfies the usual energy momentum conservation. Right? The ordinary derivative acting on T mu nu equal to 0. So that's the way you calculate the total energy that is carried away by gravitational waves.
How does this transfer happen from massive objects to the curvature of?
Through Einstein's equation, right? Einstein's equation itself knows about the energy momentum conservation, right? So it will happen. Well, I don't know what to mean by some scale. It will Einstein's equation basically. I mean, if you just follow the Einstein's equation, if you solve the full nonlinear equation, right, you will find that the orbits are actually slowly coming together. Right, once you take into account everything, all the back reactions, etc. But this thinking of this as due to gravitational wave emission, right, gives you an approximate picture which is easier to calculate. Right, you don't actually have to plug the whole thing in a computer and solve the system. Right, you just think of this as weak gravity, right, just Newtonian orbit. Right, think of this as providing a source for gravitational wave and calculate the gravitational wave emitted from the source. Right. From that perspective, it will be at least the leading order. Right, it becomes very similar to just what happens for charge particle. Right, an accelerating charge particle moving on a surface